Hello, AP Environmental, and welcome back to another exciting episode of Environmental Systems. So, this will be a very quick story, so gather around the pond, my little tadpoles, as we venture into environmental systems. Remember when we talked about that impounded water behind the dam? It's sitting there, it's quiet, it's still, and it's not moving. It doesn't seem like it contains a lot of energy, but in fact the water contains a great deal amount of potential energy. And if you release it, the water going through the gate, once you open the gate from the dam, it's going to rush out. All that potential energy of that impounded water becomes the kinetic energy of the water rushing through all of the gates, through the dam, and flowing downstream. All right, this illustrates the first law of thermodynamics, which states that the energy is neither created nor destroyed. It can only change from one form to another. And the first law of thermodynamics dictates that you cannot get something for nothing. When an organism needs biological usable energy, it must convert it from an energy source like the sun or food. So the potential energy contained in firewood never goes away, but is transformed into heat energy permeating through the room when you burn wood in like a fireplace. Same as this car here, which you use a car to show the first law of thermodynamics, as a law in action through energy conversion. So if you think of this car, including the fuel tank that's inside of the car, as a system, then the potential energy of that fuel, the gasoline actually, is converted into kinetic energy when the battery supplies a spark to the gasoline in the presence of air. All right, and so this gasoline combusts as a result. These gases expand, pushing the pistons in the engine, converting that into a chemical energy inside of the gasoline to a kinetic energy, and the moving of the pistons. So energy is transferred from the actual pistons to the drivetrain, from the drivetrain to the wheels, which propels the car forward. So the combustion of gasoline, it also produces heat, right, which dissipates into the environment outside of that system. So the kinetic energy of the moving car is converted into heat and sound energy as the tires create a frictional adhesion or a frictional rub up against the side of the road, and the body of the automobile moves forward through the air, technically. And when brakes are applied to a stop the car, friction between the brake parts releases heat energy. So no energy is never, really destroyed in this example, but it is chemical energy, and it's converted into motion and then into heat and then into sound. So just notice that some of the energy stays within the actual system itself, and then some of it leaves. Then you can think of a living system just like this, all right, where there's multiple components where energy is constantly being transferred, some staying in the system and some leaving the system. We have seen that how potential energy of gasoline is transformed into kinetic energy through moving pistons in a car engine. All right, but some of that energy is converted into a less usable form. In that case, heat. Heat is the non-usable form of energy in that whole car system. The heat is created, and that is called waste heat. And that meaning that it is not used for anything that's useful inside of that car system to do work. And that's just inevitable. So this is like natural law that when you produce work, sometimes you lose energy in the form of heat. So the second law of thermodynamics tells us that when energy is transformed, the quantity of energy remains the same, but its ability to do work is diminished. And we call that energy efficiency. And it is the ratio of the amount of energy expanded in the desired form of the total amount of energy that is introduced into the system. So two machines or engines that perform the same amount of work, but they use different amounts of energy to do that work, they have different energy efficiencies. So in my example here, I have a coal-burning power plant. So this modern day coal-burning power plant can convert 1 metric ton of coal containing 24,000 megajoules of chemical energy into about 8,400 megajoules of electricity. And since 8,400 is 35% of 24,000, this means that the process of turning coal into electricity is about 35% efficient. And the rest of that energy from the actual coal, the other 65%, is lost as that waste heat that we've been talking about. And so in electrical transmission lines between the power plant and your house, for example, 10% of those electrical energies contained within that line from the plant is lost as heat and sound as it's transported from the actual plant to your house. So we know that the conversion of electrical energy into light in incandescent light bulbs is about 5% efficient. And so the rest of the energy is lost as heat. So from beginning to end, we can calculate energy efficiency of converting coal into this incandescent light by multiplying some individual efficiencies. So here we have in our photo here, coal electricity at 0.35 or 35%. And if we multiply that times the transport of the electricity, 90%, and times the actual light bulb efficiency, 5% or 0.05. We multiply those numbers together, we get 0.016. So this calculating in this diagram is 1.6% efficient. And so that's how they got that number from calculating here to here to here. And we multiply all those together, we can say that this whole process is 1.6% efficiency. That means that 1.6% of the energy is lost to heat and other transformation. This is terrible. That's terrible. That is not very good odds. So the definition your physics teacher wants me to give you for the second law of thermodynamics is a couple of things. Entropy, energy quantity, and energy efficiency. So the ratio of the amount of energy expended into the form that you want to the total amount of energy that is introduced into the system is energy efficiency, which we just demonstrated a calculation for you. And the energy quantity, the ease at which the energy source can be used for work. And remember, there's a work formula. And entropy, the randomness contained within that system. And what I mean by randomness is always increasing in a system. Like everything is, you can think about it as moving towards disorder. So unless new energy from outside the system is added to create order, then randomness will constantly continue. And this should be a little bit more evident from one level to another. And you should be able to see this and measure it